not just last time, but before, are aware, usually in these I try to keep, to sprinkle in some like actual technical calculation of some sort, just so that you can know there's like rigor underpinning a lot of these ideas. Hands off, that's the good stuff.
I want to review.
You're stinking up the front of the room with that spaghetti, man. You're already down on my list of favorites. All right, so, but anyway, so today I'm not so much going to do that, in part because the technical things that I would do in this discussion, I actually did in the spring. And so you could go and look at the videos in the spring if you want. And it's largely just deriving equations of motion from action principles for various cases, point particles, non-relativistic, relativistic, etc. And then also when we get on to path integrals, I actually derive the form of the path integral for a point particle starting from the transition amplitude and the Hamiltonian formalism. So I'm not going to do that today, and hopefully that'll abbreviate things so I can get finished, so that next time we can start the topic we want. So we left off talking about differential forms, having introduced the notion of what differential forms were, and then talking about the arithmetic of differential forms, in particular how to add them, and then also how to multiply them using the wedge product. So now we have arithmetic, and then we turned to calculus, and so the question was, how do we take a derivative of a differential form? And of course the rule in all of this, or the guiding principle in all of this, in particular for the wedge product and derivative, was you want it so that if you multiply two forms, you get a form. So that required us to do the wedge product. And then if we want to take the derivative of a form, we want to get a form back, and that required us to introduce the exterior derivative. So we've got derivatives on the table. Now the question is how do you do integration? And I should say, and this was a topic that we talked about last semester, but the derivative and I think I mentioned this at the end of the last lecture, but the exterior derivative has this nice property that the exterior derivative acting twice on any differential form is automatically 0. And so what that means is that d squared is what's called a nilpotent operator, and a nilpotent operator, so you can kind of think of d squared as being 0, although it's technically not the same. But a nilpotent operator allows you to define something called a cohomology associated with it, and then the cohomology associated with the exterior derivative operator is the basis of what we call de Rham cohomology, which you can use to identify topological invariants of spaces. And we did a whole lecture on using de Rham cohomology to explore topological invariants last semester. So, so that's an interesting property of the derivative and its connection to topology. And we're going to find something similar for integration. So, and by the way, if you have a question at any point, just yell it out. I'm not that formal. Okay, so before we talk about integration directly, it's going to be useful to look a little bit more thoroughly at our expressions for forms, because most of what we've talked about so far has been in the context of just looking at the components of differential forms, and we haven't really worried about what are the basis forms that we're expanding our differential forms into. And so what I want to do is I actually want to identify what that basis is. So the string of logic, which people who took GR, general relativity, are very familiar with, it goes as follows. So you start with what we might call the protovector. And the protovector is basically a single vector that you can define whose properties you kind of intuitively have some understanding of. And so the protovector that we started with in GR was just a displacement vector delta S. And just to remind yourself that it's a vector, you put a vector sign over it. And the components of delta S are coordinate differentials delta x mu, or intervals delta x mu, and then a set of basis vectors, one for each coordinate in your space, okay? And these don't have to be normalized to 1. You can normalize them to 1, in which case you do something like that. but we don't necessarily have to do that. So, what we have in mind here is the analog of if I just have some arbitrary displacement vector, so this would be a delta S vector, then I can break that up into a delta Y, a delta X, and a delta Z, and then the displacement vector is delta X I hat plus delta Y J hat plus. Okay, that's the notation you're familiar with. This is just a little more general. It says the basis vectors are called this, and the components are called this. And then you do this nice string of argument, which again we did in GR, and I'm not going to repeat that here. You could always look up my GR lectures. But you start with this protovector, and then you use the definition of a dual vector. And the definition of a dual vector is that if you have a basis vector and you let it be eaten by a dual vector, so this is, or a dual basis vector, then the result is just the delta function in the indices. So what we find is this is a number. It's 0 or 1, depending on whether mu and nu are the same or not. And this is a vector. So what we find is that a dual basis vector is taking a vector and returning a number. So dual vectors are maps from vectors into the numbers. Okay, that's a way to read this, and that's the way we define dual vectors. Yes?
How is that different from like an orthogonal eigenvector? Just take the dot product.
So the question is you're talking about a dot product when you use the word orthogonality, and the dot product we think of as an operation between two vectors, but in truth what the operation of a dot product entails is it takes this vector and dualizes it, and then the dual vector and the vector combine to give you a number. So there's a more abstract but much more generally applicable way of thinking about dot products, and that is you have a set of vectors and then you have a set of dual vectors, and if you grab one of the vectors and one of the dual vectors and combine them, you get a number. Clearly the dot product fits into that because you can start with a set of vectors, you can take two of them, map one of them to its corresponding dual vector, and then take that dual and one of the other vectors, combine them to get a number. So this is just not forcing us into that language of dot products, it's just recognizing this dual space. And this is something that you see in StatMech when you talk about dual lattices and lattices. The whole idea there is that you've got a set of positions, and then you've got a set of dual positions, so that when you take the dot product, which is just a combination of one of each, you always get, say, an integer if you're looking for an integer lattice of positions or something like that. So this notion of dual pops up in a lot of contexts. So yes, it is tied to the inner product and notions of orthogonality. Okay, so with that in mind, if these are the basis of vectors, then these are going to serve as our basis of dual vectors. And what's interesting about these is that they take an interesting form. So first of all, the one thing we have to realize about a differential form, and this is also true of a vector, and it's not something that most people come into, for example, GR really appreciating, but a vector is a coordinate independent quantity, right? If I get in my car and I drive north on 93 towards Boulder at 60 miles an hour, I don't care what coordinate system you use, that's my vector, right? If you pick one coordinate system, my velocity vector might have certain components and associated basis vectors. If you pick a different coordinate system, I would have a different set of basis vectors and my velocity vector would have different components, but you're still describing the same arrow going up the road, okay? So that means that a vector is secretly coordinate independent. If you do a coordinate transformation, these transform, but these also transform in such a way that this combination overall doesn't change. And physically that makes sense. Vectors live in space and they're independent of coordinates. Well, forms work the same way. Okay? And so to identify or see readily the way that forms are independent of coordinates, we can actually identify exactly what these basis vectors are. And so without any further ado, I'm just going to write a full version of what a form looks like. So for a p form, we have 1 over p factorial, and then we have the components. Okay, these are the things we played around with a lot last time. And then the basis is the set dx mu1, dx mu p, okay? Where these are coordinate differentials. Now, why I call it dx mu is essentially because I can figure out how, so here's the string of reasoning we used in GR, but I'm not going to do it in detail. So what's nice about this protovector is that we know how the components transform because we know how coordinates transform, and these are just coordinates. So you know before you start how these things transform. Then you say, I want this to be invariant, and so you figure out how this transforms. Okay? If you know how one thing transforms and you want the product to be invariant, then you can figure out how this transforms. It basically transforms inversely to this. Now, once you know how this transforms, you can come down here and say, I want this to be invariant. I know how this transforms. I can figure out how this transforms. And it turns out that this thing just transforms like coordinate differentials. Okay? Now, this set of dx, or products of dx is not as simple as it looks because, for example, if we just consider a 2 form, then one thing we can do is we can switch mu and nu everywhere. That's just a label, right? So if I switch mu and nu everywhere, I get this. It's just a label. I can switch labels if I want. You know, I could have called this happy face, sad face, sad face, and then just turn the world upside down. Okay? You guys are not Toys R Us kids, right? Okay. Anyway, all right.
You still have to name everybody's eyes.
So this is just a relabeling. However, I can relate the components of this to this by interchanging these indices. Now that's not a relabeling. That's an interchanging of indices. But what happens if I flip these indices on the components of a form? So,
Minus sign.
yeah, you get a minus sign. Remember, forms are anti-symmetric if you swap indices. So this is equal to minus 1/2 a mu nu dx nu dx mu. But what that means is for this expression to be equal to this, if I swap the order of these, then I need to pick up another minus sign. So this sort of naively simple looking product of coordinate differentials, it is a product of coordinate differentials, but it's anti-symmetric if you swap any two of them. Okay? In fact, one way that you can write this to make that clear is you can literally write dx mu 1 wedge dx mu 2 wedge ... wedge dx mu p. Because after all, these are forms. I mean, you're expanding a form in terms of components with a basis. This is a basis of forms. Okay? Now, I'm saying all this because this is going to play a very important role in integration. Okay? Okay, so why is this interesting? So let's consider a coordinate transformation. So let's consider if we were doing an area integral, and the measure of our area integral was dx dy. If we did a coordinate transformation to some new coordinates, x prime that we can express in terms of the old coordinates, and y prime that we can express in terms of the old coordinates. So if we do a transformation to a new set of coordinates, then the area measure dx dy transforms to a new expression dx prime dy prime, and we know how to calculate that. We just do a series of partial derivatives. I can feel the sweat running down my back. This is so gross. Oh, God. All right. Ugh. So nasty. It's so gross. Okay, anyway, sorry. If I get like a big sweat patch on my back, you guys just ignore it. We'll edit that out with Video Shop or whatever editing tool you use to do this. Okay, all right, so just multiplying this out as quickly as I can so that we can see exactly what's happening. Okay, so that's literally just multiplying out that expression, okay? But by the way, the thing in parentheses here is the expression for dx prime, okay? It's just expressing dx prime in terms of dx and dy. And then similarly, this is just an expression for dy prime. And then I just bang that out, okay? However, we actually know what the answer to this should be because we know how to transform measures of integrals, okay? They should transform with the Jacobian. So this should be equal to dx prime dx, dy prime dy, minus dx prime dy, dy prime dx, dx, dy. That's what it should be equal to, okay, based on things we learned in calculus about doing area and volume integrals and then transforming coordinates and re-expressing those things, okay? All right. So what we notice is that this actually works provided that dx dy is minus dy dx. Okay? If dx dy is minus y dy dx, I can flip these two terms, pick up a minus sign. That's exactly this. Okay? But then you might ask, well, what about these terms? And here we get something a little weird. Because if this is true, if I take any two coordinate differentials and interchange them, I get a minus sign, then this immediately implies that dx squared and dy squared are 0. Because you would have to be able to say this, which means that it's 0. Okay? So what we are seeing is that the anti-commutativity of these coordinate differentials, okay, are actually acting like an integration measure. Clearly this is going to be key to the integration of forms. So what we find is that at the end of the day, the basis of p-forms, that is this set of stuff right here, understood as this, is a measure for integration over a p-dimensional oriented space. Okay, it's actually behaving like a proper measure. All right. So I threw in this word oriented here. So let me come back and talk a little bit about oriented and what this has to do with orientation. It's so confusing that we start this on the half hour because I look at the clock and think we got 8 minutes left. And I'm still on the first page. Okay. So, you awake?
Yeah.
Because I'm going to have a question for you.
Shit.
Good. That is not appropriate. Again, I'm in a tank top, so we throw all propriety out the window.
This video is going to need a lot of editing.
Okay. So orientation. So when we talk about a space, and we want to talk about the orientability or the orientation of that space, what we're talking about is essentially signing areas or volumes. And by signing, I mean applying a plus or a minus to it. Okay. So what do I mean by this? So you can imagine if we had some two-dimensional surface, then if we wanted to identify the area of this, we could say, if I'm talking about the area of this side of it, I'm talking about an area we'll call plus. But if I'm talking about the area of the opposite side of it, I might be calling that an area minus. All right? Now clearly this does not work for the case of a Mobius strip. Let's pretend that's a Mobius strip. Because what's weird about a Mobius strip is it's only got one side. Because you can start at any point and you can move along the circle of the Mobius strip and you will end up on the other side without having gone over an edge. But that means if you assign this side to be plus, it's plus all the way around. So both sides of the Mobius strip have the same sign, which means that you can't distinguish one from the other. Okay? But we all know one way to describe a Mobius strip is that it is an unoriented surface. You cannot do this with a Mobius strip. Okay? Now, a way that you could do this, if you were silly, is you could, first of all, take this space and, for example, define its area by breaking it up into little infinitesimal pieces, with some coordinate system x and y. And then we could talk about the magnitude of the area being the magnitude of the product of these coordinate differentials. Okay, so right now I just got a positive number, and then what I want to do is I want to assign a sign to it. Am I on this side or that side? And then the way that we could do this is we could set up a third dimension, call it z, and then we can say that our area vector, in this case it would be a differential area, because we're talking about coordinate differentials, our differential area vector is given by a unit normal vector times the magnitude of the differential area, and in this case, where our surface is sitting in the xy plane, then the normal vector is only going to have a component along the z-axis, and so this is going to be, can't remember my basis vectors in rectangular coordinates, it's going to be something like that, right? So whether I'm along the positive or the negative z changes the sign of this vector. Actually, so we can say this, sorry. And so that's a way to assign a sign to this thing to give it an orientation. Okay, you ready?
Sure.
Why does this suck?
Because we have to arbitrarily decide which one's positive and negative.
Well, that sucks, but why does this really suck?
I don't know. Why does this?
Why
really
does
suck?
assigning a normal vector to a plane, why is that a bad idea? Last Friday.
Because it was something about how when you're in not 3 dimensions, that gets weird.
Exactly. Assigning a normal vector to a plane is only a unique assignment, good job, in 3 dimensions. If you're in 4 dimensions and I take a 2-dimensional plane, there is more than one orthogonal direction. Okay? So the whole idea of normal vectors kind of blows up if you're in more than 3 spatial dimensions, and so we tend to avoid that. Well, the good news is we don't even need it, because if I consider a differential volume and I've got an x and a y coordinate system, forget about z, so I've got some dy and some dx, then I can just use the order of the differentials themselves to provide my orientation. Okay? So in this case, I might say that dx dy, which I think of as going this way and then up, is what I would call, if we were thinking about normals, I would call it the outward normal, but we don't need that. And on the other hand, if I go dy dx, then I'm talking about something going inward, but I really don't need to think about these things. I can just assign plus and minus to these and be done. Okay? So what I'm getting at is the fact that you're commuting these differentials and picking up a sign is exactly what's allowing us to allow this to encode orientation in our surfaces and volumes. Okay? So at the end of the day, at the end of the day, if I write an expression like this, what's so funny, is the sweat showing up?
No.
Okay, if I write integral AP over a submanifold sigma p, or a space sigma p, this expression is well defined. And it's coordinate independent. I don't need to d anything, because the measure of integration is built into AP. It's this set of basis 1 forms wedged together. Okay? This is not bad notation, like Physics 1 students are off to use. What are you integrating with respect to? Oh, dt, dx. No, this is actually perfectly well defined. The integration measure's there, hiding. Okay? And it's coordinate invariant because the form itself is invariant. I can use any coordinates I want to express this. Okay? All right, so what's interesting about this is that what this allows us to do is to take a space, so say we live in, 3 plus 1 dimensions, 10 dimensions, it doesn't matter, and take some subspace. So take like a curve, okay? So this might be a one-dimensional space, a one-dimensional subspace. So this would be a sigma 1. What it does is it gives us a coordinate invariant thing that we can associate with this curve, and that would be the integral of a 1 form over that curve. Alternatively, if we took a 2-dimensional surface, we could integrate a 2 form over it, etc., etc. These integral expressions are perfectly well defined without having to rely on coordinates. All right? Well, there's something actually very deep about this in physics, because what it tells us is that if I were writing down for example, a Lagrangian to describe some dynamical system, and I wanted it to be coordinate invariant, I can actually write this term down as part of my Lagrangian. And it's invariant without anything else. But what this means is that there's a natural coupling between this 1 form and a one-dimensional line, which is what you would see if you had a particle sweeping something out. Here you would have a natural coupling between a 2 form and a 2-dimensional surface. So for example, if you had a string and it moved in time, it would sweep out a 2-dimensional surface. And there's a natural coupling between 2 forms and strings. And then you can generalize this up to p forms. And then in the context where we actually see these extended objects, those are natural couplings between p forms and d branes. So the forms come in as sort of the fields that are associated with objects of various extent, be it particles, strings, d branes, etc. Okay? And that's obviously going to become a very important story in topics we'll cover later when we talk about string theory, dualities, etc. Now, to get back to sort of more mundane things, one way to appreciate the power of differential forms is to consider the following. So first of all, for an orientable p-dimensional manifold sigma, so this is an orientable p-dimensional sigma, we have the following result. We have that if I integrate a p minus 1 form over the boundary of sigma, so that partial just means you're looking at the boundary. So sigma is something like this, and then the boundary is indicated like that. If we take a p minus 1 form and integrate it over the boundary, then in general, this is equal to the integral over the entire space of the exterior derivative of the p minus 1 form. Okay. So it allows us to relate the integral of something over the boundary of a space to the integral of the derivative of something over the entire space, where this is obviously generalizable to any number of dimensions. Okay. And this is a coordinate invariant result. What we call this. if you were going to give it a name.
Divergence theorem.
Stokes' theorem.
You would actually call it Stokes' theorem. I heard several different things pop up, and they're all right, except for path integrals. Sorry, Joe. But we'll get to path integrals. The truth is that you can take this version of the Stokes' theorem, and by considering various cases of the numbers of dimensions, and then doing an operation we'll learn later about called dualization, you can actually, from this single expression, derive the more familiar version of the Stokes' theorem that you see in E&M. That's actually called the Kelvin-Stokes theorem. You can get to the divergence theorem, and you can get to the fundamental theorem of calculus. All of them follow from this one expression. Okay? Just by looking at special cases.
So this integral over just the boundary of the shape, will that give us the same change in p as doing that derivative? Because these both have to be of the same form, right?
These are both
level of
numbers.
p.
Each side of this is a number,
Gotcha, okay.
right? Because this is an integration over a p minus 1 form over a region which is p minus 1 dimensional, because sigma is p dimensional.
Yeah. Gotcha, okay, cool.
Do the dimensions have to match? Like,
Sorry,
could you
yes.
do like,
on the
Yeah,
right
you
side,
can't
is it should be a derivative of a p form or a p minus 1 form?
Oh, sorry.
Yeah, that's right.
No,
that's right.
no, that's right. Because if I take the derivative
Oh,
of the
then
p
it does
minus
p
1
minus
form, the derivative raises the degree.
And it's over this.
Yeah, this isn't like derivative of x to the n. This is the exterior derivative actually raises the form degree to p, so it's a p-dimensional form at the end, and then you can integrate that naturally with a p-dimensional manifold.
so why can't you do like, you can't be like A4 over like sigma 2?
A4 over sigma 2.
Like if sigma had dimension 2 and A had dimension 4, you can't do that integral.
Well, you can define. Okay, so you can define other integrals. Like you
Okay.
can you can integrate a form over other manifolds. But the thing is if you do that, then the measure isn't going to work out.
Okay.
Okay. So for example, I could take like a 4 form and I could integrate it over a 2-dimensional space. The answer will be a 2 form.
Mhm.
Because I will have basically gotten rid of 2 of the degrees of the form through the integration.
Okay.
If you want to integrate a 2 form over a 4-dimensional space, you have to add extra elements to the measure of integration because the 2 form isn't defined naturally over the 4-dimensional space.
Okay. So I guess that kind of answers the question, but like you couldn't include this to go like another form, another dimensional form less, because you would have 2 derivatives on single A, and that makes 0, right?
So in this case, the outer derivative is not the inverse of the integration.
Right.
Because, yeah.
Okay, all right, so in the interest of time, and actually getting to our first new topic next week, now I'm going to do a lightning review of path integrals with a primer rooted in all the other junk we do in physics, and that is
Chemistry?
I said the junk we do in physics. I didn't say.
So
that was outside of our
for a
house.
transition then.
Okay, so very quickly, because I think it's important to kind of understand how we use things in addition to just defining what they are. So very quickly, first of all, you're all aware from Physics 1 of this, and that represents an equation of motion that's second order, and the derivatives with respect to time popping up in the acceleration. And then in order to use this, we usually assign some boundary conditions. Okay, we need 2 boundary conditions. We can give the initial position, the initial velocity. You can give other boundary conditions if you want. And then you solve the second order differential equation, and the solution to that is the unique path of the object that you're considering. Okay, so with boundary conditions, you can solve for the path in time. And once you have this path in time, everything you want to know follows from it, because you could take the derivative of that function and get the velocity, and then you can take the second derivative and get the acceleration. So it's all That's sort of the framework of mechanics circa physics 1, which I hope we're all relatively comfortable with. Okay, so then you get to physics 350, and you find a new formulation of mechanics where you say, okay, I'm going to consider this thing called an action, and the action for a point particle is going to be defined as the integral of a Lagrangian, which is a function of the generalized coordinates q, so you could just use rectangular coordinates and say these are x, y, z, and their velocities q dot. And then what we do with this thing is we take its variation, set it equal to 0. And again, what we're talking about when we talk about a variation here is we're talking about taking a particular trajectory and varying it. So we take the trajectory, we give the trajectory plus some deformation. But this is subject to the vanishing of the variation at the endpoints of the trajectory. Okay, and that's a very important property that we use when we actually explicitly work out what this variation is. And if you do all that, at the end of the day, what you find is that the trajectories that actually satisfy this extremization condition also satisfy the Euler-Lagrange equations of motion. Okay. And again, this is one of those steps that I did in detail the last time we covered action principles and so forth, so you can go back and look at my notes on that, or you can watch the video. Okay, and this is a really simple thing. You just do an integration by parts, and then use these vanishing variations at the endpoints to get rid of the boundary term, and you get Euler-Lagrange out of that. Okay. So how do we use this? So we've got kind of two ways that we can use it. One way that we can do it is we can we can specify, or one way that we can do it that's kind of aligned with this is we can specify Q of Ti and Q of Tf. So that is, we can start with this point here, Q of Ti, say I'm there, and then I want to go to there. And then we can solve this differential equation, which is just an equation of motion, and that will give us the unique path, the unique classical path which connects the initial and the final point. Another way that we typically use it is to specify Q of Ti and again the initial velocity. So we specify Q of Ti, Q dot Ti. And then solving this differential equation telegraphs the motion out of here. So we can actually find the motion at any point. Okay, we'll just get a functional solution. Okay. Either way, you're supplying two boundary conditions to solve what's generally a second order equation. And it's second order because of that term. All right? So you've got equations of motion from physics 1. You've got action principles from intermediate mechanics, which of course at the end of the day give us equations of motion. So it's kind of the same story. But of course there's huge advantages to this because, for example, among many other things, when you work with a Lagrangian formulation, you're free to pick whatever coordinates you want. And so if you have a system with constraints, it's nice to pick coordinates so that you get rid of superfluous degrees of freedom that you don't actually experience because of the constraints. So you know, if you are on a roller coaster moving on some curved surface, in Newton's second law, you have to use something like that, and it's a two-dimensional problem, but with the Lagrangian, I can define my coordinate as distance along the track, and that reduces it to a one-dimensional problem, which is perfectly consistent with the Lagrangian formulation. So you can reduce two-dimensional problems to one-dimensional problems, et cetera, just by a clever choice of coordinates. It's also really nice if you want to encode the symmetries of a system. All right. So this is non-relativistic. You can relativize it, okay? But in the process of relativizing it, you might as well actually go one step further and actually introduce the notion of a field. Because it turns out if you're ever going to quantize anything with relativity, you've got to introduce the notion of a field because of this sort of conflict between conservation of probability, that the norm squared is equal to 1, the norm squared of the wave function is equal to 1, and the fact that in relativity you can create and destroy particles. So the particle number is not conserved in relativity. So the natural way to incorporate that is in a relativistic theory of fields. So instead of the Lagrangian, we instead consider the Lagrangian density. And the natural generalization is that in non-relativistic point particles, you have a particle and you're interested in its trajectory, x of t. And this could be x mu of t if you're in more than one dimension, I should say. Here, instead of thinking of a particle moving in space-time, we actually define a function everywhere in space-time. So this phi is a function of where you are. And then the configuration of this field is the dynamics. So what we have in mind, just to kind of connect it to this, is suppose I have a function phi of x and t. Okay, so I've got an x and a t-axis. And this thing is defined everywhere here. So it's the value of phi is going to come out of the board. So I'm going to plot it out of the board. Now just imagine that everywhere on this board phi is 0. So this function is just trivially 0, except for a localized line. So phi is 0 everywhere, and then it just kind of comes up to a little skinny line, right? That's exactly what that is. Okay. So we can recover particle physics from fields just by looking at localized solutions. Okay. But you can do more general things if you're willing to work in terms of fields. And then there's a lot of value to fields, which we're not going to have time to cover. Okay, so what I'm going to do now is just sort of take what we talked about here and just write down what its generalization is here. So first of all, you'll notice the coordinates get replaced by fields. So these are the degrees of freedom. You can move in x, y, z. The degrees of freedom are the fields you have. How big is the field at each point? The derivative of the coordinates gets replaced by the derivative of the fields. That's just an analogy, but it's actually the way it rigorously works out. Okay? The action, instead of integrating a Lagrangian with respect to time, we have to integrate over all of the coordinates. So this is where you actually get a relativistic invariance, and this becomes the integral of L phi d mu phi over, for example, if we're in 4 dimensions, d4x. And you can show that applying the principle of least action, that is that the variation of this action under a deformation of the fields which is constrained to vanish at some boundaries, that the variation of that action is 0, results in the Euler-Lagrange equations, but this time for the field Lagrangian. Okay, now, again, proceeding by analogy is always nice. This is the Euler-Lagrange equation you're familiar with. And if I literally just make all the replacements, I replace the coordinates by the field, that's that term. Derivatives with respect to time become derivatives with respect to all the coordinates. That's exactly what happened when we came from here to here. Okay? So this d by dt becomes the d by dx mu. And then the derivative with respect to the generalized velocity is just now a derivative with respect to the derivative of the field. Okay? Again, you know, this is rigorously defined. I'm just showing it to you by analogy to connect it to something you're familiar with so that we don't have to take the time to try and do this. And of course, you can take this Lagrangian, and if you want, you could, for example, take your Lagrangian to be 1 over 16 pi F mu nu, F mu nu. And if you write down the Euler-Lagrange equations associated with that Lagrangian, what you'll actually find in the end is half of Maxwell's equations.
Come on, man.
Okay. All right. So that's sort of classical physics in a nutshell. Now what we're going to talk about is quantum. Any questions about this before I move on? I know I'm going kind of quick, but again, a lot of the details here are filled in lectures we did last spring, so I don't want to spend a lot of time repeating lengthy things. Okay, so now we're going to go to quantum, which I think is where you're all familiar. The idea of the path integrals become important. So when we move from classical physics to quantum physics, we obviously know that the questions we ask change. So in the classical case, we can be given a Lagrangian or a Lagrangian. So this script L is called a Lagrangian density as opposed to just a Lagrangian, but I'll just use the word Lagrangian to correspond to all of it. Or let us not forget that you could also do all of this in the language of Hamiltonian mechanics. So you provide a Lagrangian, and that's the definition of your mechanical system. And then for a specific calculation, you set boundary conditions. So again, one nice set is to give the initial position and initial velocity, and then you predict the future. Okay, it's deterministic. So you can, for example, set the initial position, you can set the initial velocity, and then this thing right here is finding Q as a function of time. That's predicting the future. Okay? Nice and classical. Okay. If we move to the quantum version, some of it plays out just the same. So for example, we can define a quantum theory starting with a Lagrangian, or as you're more familiar from your quantum courses or Hamiltonian, you can always move back and forth between the Lagrangian and the Hamiltonian descriptions. And let me just, for the sake of being concrete, say I'm going to set initial conditions here. Okay? And then you can set initial conditions okay. However, there's a difference. And the difference comes here. In classical physics, it's perfectly well defined to give me the initial position and initial velocity of your particle system, whatever. However, in quantum, we know that these are incompatible. I can't give you the x position of something and tell you its x velocity to arbitrary precision. Okay. So instead, the best we can do is give one or the other. Now what that means is that when we take our equation of motion to predict a path, and let me actually, we get paths instead of a path. Predict paths. Okay? So now our outcomes are many. Okay, because we can't uniquely specify all of the initial information. And then this set of paths that we're considering are essentially all paths which are compatible with the statement of our definition of the mechanical system and the prescribed boundary conditions. Okay? So to get these paths, you do something very similar to what you do here. You just don't get completely uniquely determined solutions. because you don't have completely prescribed boundary conditions. Okay, so typically what we do, it's actually not that bad. It's not going so bad. Okay, so typically what we do when we work in quantum mechanics is we start with some initial state. Okay, and we're just going to now, instead of talking about initial position or initial velocity or anything like that, I'm just going to say initial state, because we know that in quantum mechanical systems, the description of the system can become very abstract, and so generically we just throw the word state on there. Okay, this could correspond to a particle at this position. But we take an initial state and we time evolve it with an operator. And this is where, of course, most of you see the value of the Hamiltonian formulation of classical mechanics, because it plays nicely into this particular formulation of quantum mechanics. So we have this unitary time evolution operator that's constructed from the time that you want to evolve in. So we've got some time interval from Ti to T final, and then you just implement it with the Hamiltonian. So the Hamiltonian, and this actually goes back to classical mechanics, the Hamiltonian operator generates flows through this sequence of continuous canonical transformations in phase space. It generates the time evolution of the system. That's a classical statement. If you have a quantum state and you want to time evolve it, you still use the Hamiltonian for that. Okay, but the Hamiltonian is now promoted to an operator, so anytime you see positions and momenta in this Hamiltonian, you've got to have non-commutativity between them. That's the difference between this and the classical Hamiltonian. And so at the end of the day, you might be interested in calculating something like this, where you say, I want to know what is the probability of evolving from the initial state QTI to some final state QK at T final. And then if we take the magnitude squared of that guy, then this is the probability associated with this particular outcome. So for each of these particular paths, we can say, all right, well, this path has got some final position, Q1 T final, T final, T final. And to figure out the relative probabilities of these things, because we know in quantum mechanics you don't get a unique answer. You get all possible answers that are compatible with this prescription defining your system. You get all possibilities, but they get different probabilities associated with them. And this is how you go about calculating those probabilities. And we can think of this thing as the amplitude to go from Q at Ti to Qk at T final. Okay? And our abbreviation for this will just be Q final e to the minus h hat T Q initial. Okay? So if you haven't taken quantum mechanics, this is not obvious. It's not clear, it's not comfortable, it's not anything, okay? But this is something which you will do a lot in quantum, okay, the first time you take it. So, one of the things we know is that when you do quantum mechanics, the big difference between classical and quantum physics is when you do classical physics, you ask, what is the answer? What is the system going to do? And in quantum, you say, I have a set of possible behaviors of the system, and I want to assign probabilities to each of them. And then if I set up a bunch of replicas of the same setup, so an ensemble, and I do measurements, I will find that Pn number of times I will get this particular outcome associated, the number of times associated with its probability. Okay? So that's sort of the philosophy of doing quantum mechanics. Now, there is a whole page of technical calculation which I'm going to skip. Okay? I'm so happy. And that whole page of calculation is demonstrating exactly this expression, that this time evolution, and I've thrown out factors of h bar, which I'm now going to restore, whenever we do quantum mechanics, you should always ask yourself, where the hell is h bar? Well, I just conveniently left it out. Again, this is in the lecture from the spring, but this entire page derives the following result. This thing is essentially an integral over the paths connecting Q initial to Q final, where each path is weighted by an exponential, which is given by this expression. And we have in mind here that we have some kinetic term, and then we have some potential, which is driving the dynamics of our system. And then we, of course, recognize that as the action. Okay? So this is the Lagrangian. We're integrating it over time. That's just the action. Okay? So literally, to get from here to here is an entire page of stuff, and it involves all the love of quantum mechanics. So you expand into complete basis, and you're inserting the resolution of identity in terms of momentum states and position space and position states. So there's lots of good stuff in there, but at the end of the day, this quantity that we're used to calculating that gives us probabilities can instead be recast in terms of this expression, which is different in a couple of ways. First of all, it integrates over all paths, and it utilizes the Lagrangian instead of the Hamiltonian. Okay? This thing is called a path integral. Does anybody need to get up and walk out? I'll be done in like 5 minutes. Okay. So that thing is a path integral. What it calculates for us is exactly what we would have calculated from our more familiar tools of quantum mechanics. It's more powerful in a variety of ways. First of all, because it's based on the Lagrangian, you get all the advantages that you get with Lagrangian mechanics. So, for example, if you have a constrained system, you can reduce to generalized coordinates so that you only have to worry about the degrees of freedom you can actually move in. More importantly, if you have symmetries, encoding the symmetries in a Lagrangian is much more straightforward than in a Hamiltonian. For example, space-time symmetries. If you're doing relativistic stuff where position or space and time are on the same footing, it's hard to see that in a Hamiltonian framework, because in a Hamiltonian framework, right, time is singled out. In Lagrangians, time is on par with everything else. So there's a lot of advantages to doing this, but it gets even better than that. Blue. Ooh. Feeling patriotic today. I got some red, white, and blue for you guys. It gets even better than that for a couple of reasons. So again, this path integral is not calculating the behavior of the system. It's saying I have some initial position. I've got a set of final positions that are compatible with the dynamics that I prescribed in the boundary conditions here, which of course are limited because it's quantum. And the path integral, that thing there is saying, okay, pick one of them. So that would be this guy right here, which we would think of as the upper limit of the path integral. So you can think of this as qi to q final. You pick one of them, and you actually sum over all possible paths between this guy and that guy. That's what this thing right here is doing. Okay? All of them contribute to that quantity, but they contribute differently, because what you do is you say, okay, I take one of these paths. So again, this is for one outcome. And then we have numerous outcomes, and we do this for each one of them. So each of these paths, Q, Q prime, Q double prime, etc., for each of them, we would stick it into the action. So we would integrate the Lagrangian with that particular path. And we would repeat this for each of these paths, and we would get different values of s for each and every one of them. Okay? We take all of them and we add them all up. Of course, there's a continuous distribution of them, so it's an integral. Hence the path integral. That result is the probability of starting here and ending there. Then to get the probability for this outcome, we would do the same thing, constructing all the compatible paths, and then doing the path integral for that outcome. Okay. So you can imagine this could be a laborious procedure, but I'm going to show you a very powerful shortcut in just a moment. So that's the way that we use the path integral. One thing that's nice about it is that this helps you to understand how the principle of least action works. So last spring when we talked about this, my grad student Zach Polonsky was really bothered by the variational principle, because he said, if you've got two endpoints and the principle of least action in classical physics says that the actual classical evolution is the path which extremizes this, then on the one hand, this kind of makes sense. But on the other hand, if you start out with initial conditions for position and velocity, how does the physics know that it's taking one of many possible paths and it happens to be the one that extremizes? He was bothered by that sort of, how does the physics know to pick that particular path? Like, how is it smart enough? And the nice thing is that the path integral actually explains it. In fact, this is what motivated Feynman to develop the path integral formalism. So what the path integral formalism says is, this actually tries all paths. It tries every single way to get from A to B. Okay? And each of them are weighted by this exponential. However, in the classical limit, you're talking about an action which is much, much larger than h bar. H bar has units of action if you actually look at it. So these two, and this is an exponential of I times s over h bar. Clearly the units have to disappear. So the classical limit is a limit of large action. And what happens is in the large action limit, the paths which do not extremize the action, so paths for which delta s does not equal 0, fluctuate wildly. Okay, they oscillate like crazy and they cancel each other out. The only path that doesn't get canceled out is the one for which delta s actually equals 0. But that is, of course, the classical motion of the system. So that's the classical, quantum classical correspondence in the path integral context. You just take the s, the action of the system, to be larger than h bar, and you get cancellations because of the rapid oscillations, leaving only the classical contribution. So, the true story of physics is quantum mechanics. We know that. Classical is just an approximation. So the true story is that this evolution knows about every possible path. And in the limit, you're just picking a favorite. Okay? You can take everything I've written here, which is obviously specific to point particles moving in time, and you can generalize it to fields, in which case the notation looks a little different. We have an integration over all field configurations, because we're not talking about particles moving along some trajectory, but rather what is the field configuration doing. So we integrate over all field configurations, and then we weight each one by this factor e to the I h bar, integral of the Lagrangian density. And in 4 dimensions, that would be d4x. This is just the action for the field. So that would be the path integral for fields. Okay? So again, we can set an initial field configuration and some final field configuration, although the ideas of initial and final get kind of wonky when you're doing things relativistically. So you literally just think of it as boundary conditions. And then you have many different field configurations which connect the initial and the final. Each one has an associated weight. Okay? And so to figure out the probability of this particular final field configuration, you evaluate this sum. Now here's a cool point which I did not make last spring, but will hopefully connect to something many of you know. When we use field theory to calculate things in particle physics, usually we're interested in, for example, taking little point-like particles, and so we have some initial collection of particles, and then we want to calculate some final collection of particles. So we do like a scattering experiment. We take like a proton and a neutron and we slam them together, and then we ask what comes out. And obviously the idea here is we set this, we find all possible outcomes, and then each one we calculate a probability for. Okay, that's what we do when we do high energy scattering experiments or when we look at decays. So in this case, if I were going to write down the corresponding quantum amplitude, one way to do it is to say, I'm going to start in the vacuum with no particles, and I'm going to create this guy at position x1 using a field operator. So the idea here is that the field is phi, and so I'm putting a particular excitation of phi at the position x1, and then this might be x2, and then this might be x3, x4, etc. And so in the field operator language, I'm just sticking in a bunch of factors, a bunch of field operators that are creating these little excitations. However, I start with nothing. So that's what this 0 is, it's the vacuum. I create these, and then I want them to evolve to these final states, and then them go away and give it back the vacuum. Another way to think about this is that this thing is the state phi x1, phi x2, and this thing is the state phi x4, phi x3. And you're just calculating the probability of going from this configuration to this configuration. We're just adding in this step of building it from the vacuum. Okay? Now here's the cool part. This thing right here is the definition of what we call an endpoint function. And you have probably seen these before, but they've probably been given different names. If n is equal to 2, this is what's called a Green's function. And if n is equal to 2, and the theory that you're considering is free, that is, there are no interactions, then this is what's called the Feynman propagator. Okay. But this is the thing that you want to calculate using this quantum field theory as it applies to particles. Like literally, these are the things you want to calculate if you want to go and compare with experiment or whatever. Okay? So you want to calculate these correlation functions, these endpoint correlation functions. Now, what would this look like if we did it with a path integral? Well, sadly, it would look like this. We would have an integration over all paths, and then we would have to insert these operators. And then we would have our weighting factor. And then we would have to normalize. Okay, so this quantity is this quantity right here. So it's obviously using the path integral of just e to the I over h bar s phi, but to create these excitations, you actually just do that by inserting these operators in the integrand of the path integral. And then this is just a normalization factor, okay? Now here's the cool thing. This sucks. Because it means if I pick one problem to study, I do the path integral. And if I pick different particles coming in and different particles coming out, I have to redo the path integral. And path integrals are hard. Integrals are hard, period. Nobody likes to do integrals. So what if I told you there was a way to get around it? Would you do it? Hell yeah, of course you'd do it. Okay? So imagine that you could calculate this thing. And we're almost there, guys. I know you're itching to go. I am too. Imagine that you could calculate this thing. Okay? So this is very much the path integral, but you got this extra chunk that you're adding into the action in the exponential. Okay. But let's just suppose we were savvy enough to be able to calculate this, where this is just some arbitrary function. Okay. If we could do that, then it turns out that Gn, that is the endpoint function, is given by the following, and this is the punchline. So let me point out what's nice about this. These g's are the things we most often want to calculate in a quantum field theory. Again, they just correspond to the amplitude to propagate from an initial set of particle states to a final set of particle states. These are what we like to calculate. Straightforwardly applying the path integral means we have to redo the path integral every time. If we could just calculate this quantity once, then it turns out we can get the endpoint functions by taking derivatives of this thing. Okay? Where again we see a normalization factor in there. Right? Now I want you to stare at that for a minute and tell me if that looks like anything you've seen before.
Sounds like partition function.
It's exactly a partition function. This is called the partition function in quantum field theory. So everybody remembers partition functions from StatMech. If you haven't taken StatMech, you haven't seen these yet, but when you take StatMech, statistical mechanics, you will look at partition functions in detail. But what do partition functions do for us? We calculate the partition function for a statistical system once, and then to calculate various thermodynamic average quantities, we just take derivatives of the partition function and divide by the partition function itself. So there is a perfect analogy between using this construct to calculate quantities in quantum field theory with what we do in statistical mechanics, but folks, that should be expected. Statistical mechanics says you have a lot of outcomes that are possible, that are compatible with what you're dealing with. You weight each of them by a Boltzmann factor, okay? So in statistical mechanics, you have probabilities because you're not allowing yourself to see the microscopic behavior. You're just looking at macroscopic quantities. It's classical, but you have probabilities. Here, you have no choice but to have probabilities because it's quantum mechanical. But the framework is still the same. Okay? So in quantum field theories, this idea of a partition function is the kind of object where if you could calculate it for a given quantum field theory, you've got everything you want to know. You can just take derivatives to generate all of the endpoint functions, which are the root of the things that we typically want to calculate. All right, I'm going to stop there. Sorry for running over, but I'm glad we got through that. Right?
Did you get through all of your notes?
Yes, I did.
Wow.
14 extra minutes. We did. 14. We started at 11:32.